In this video, we are going to be talking about the core section of EPA Section 608. Okay, EPA Section 608 is part of the Environmental Protection Agency Clean Air Act. Okay, this PowerPoint is not meant to be a complete presentation of the material, but it's meant to be a guide for reviewing the material related to this Section 608 of the Clean Air Act Amendment. It's intended as a part of a refrigeration training course, but not a course by itself. In other words, when you review this, you still need to learn more about refrigeration. You still need to do some studying on your own before you're ready to take the test. This PowerPoint is produced by ESCO Institute, which is one of the EPA testing agencies. So, the overview of this whole examination process and the whole process of getting certified is that federal regulations require anyone servicing, repairing, or disposing of any equipment containing a controlled refrigerant to have in his or her possession a card certifying that he or she has obtained the proper level of certification for the work he is performing. This means you cannot work under another person's certification. And I have to make that very clear. While licensing laws in some states allow you to work as a refrigeration technician under your employer's license, EPA regulations do not allow you to work under another person's certification. The other thing I need to point out here is that this EPA certification is not a license. Okay? Licensing is done on a state level. EPA certification is done on a federal level. So, if your state requires an HVAC license, air conditioning, refrigeration, whatever type of license, you cannot work under your EPA certification and call it a license. Distributors can only sell refrigerant to EPA certified technicians or a company that employs certified 608 employees. Automotive refrigerant is covered under Section 609 of the Clean Air Act. There are 4 categories of technician certification. You have Type 1, you have Type 2, you have Type 3, and Universal. Each section of the test contains 25 multiple choice questions. The technician must achieve a minimum passing score of 70% in each section that they wish to be certified in. You also must pass the core. Person Type 1 is designed for persons who maintain, service, or repair small appliances. That's like ice makers, refrigerators, anything that is self-contained. A small appliance is defined as a pre-assembled unit that's hermetically sealed and factory charged with 5 pounds or less of refrigerant. Examples include equipment such as water coolers, window units, refrigerators, freezers, dehumidifiers, ice machines, and packaged terminal air conditioning. The key to Type 1 is that the equipment must be factory sealed and have 5 pounds or less of refrigerant. That is on the test. You do need to know that. Type 2 certification, persons who maintain, service, or repair or dispose of medium, high, and very high pressure appliances containing more than 5 pounds of refrigerant, or the installation of such equipment requires refrigerant charging, must be certified as Type 2 technicians. It's important to understand the refrigeration pressure of each certification category. Type 2 certification includes medium pressure, high pressure, and very high pressure appliances. If a system requires refrigerant line connections or charging in the field, even if it is less than 5 pounds, the technician must be certified as Type 2. High pressure refrigerants have a pressure between 155 psi and 340 psi at liquid phase temperature of 104 degrees. Medium pressure go between 30 and 155 psi at liquid phase temperature of 104 degrees. Type 2 certification does not include small appliances or motor vehicle air conditioning systems. Most technicians will need to be Type 2 certified or have a universal. Type 3 is for persons who maintain, service, or repair or dispose of low pressure appliances. Centrifugals and chillers must be certified as Type 3 technicians. Low pressure refrigerants have pressures of 30 psi or lower at a liquid phase temperature of 104 degrees. Universal is people who obtain Type 1, Type 2, and Type 3 certification levels are universal technicians. In other words, you have passed all of it, the core, the Type 1, Type 2, and Type 3. You will be certified as universal technician. That should be your goal. So the test format, the core contains 25 general knowledge questions that are relating to stratospheric ozone depletion, rules and regulations of the Clean Air Act, the Montreal Protocol, refrigeration recovery, recycling and reclaiming refrigeration devices, substitute refrigerants and oils, recovery technicians or techniques, dehydration, recovery cylinders, safety, and shipping. That is all part of the core. Federal regulations require the test to be closed-booked and proctored exam. You will not find valid EPA tests online unless they're in a proctored environment where you are being monitored for not being allowed to use your books. The only outside material allowed during the test is a temperature pressure chart and a basic 4-function calculator. Phones are not allowed to be used during the examination and must be turned off and put away, not onto the desktop during the examination. All exam participants will be included in an online registry lookup by name, city, and state, as well as the certification achieved. No personal information is in the public registry. Technicians will be able to opt out of this registry by logging into the ESCO website or by contacting customer service. You will have some required information for the exam. Okay, it's for identification purposes. It's not distributed. You do need to have a picture identification. You'll need to have a social security number. You'll have to have a home mailing address. You'll have to provide your date of birth, a phone number, and an email address. The proctors are required to ask for this material. You can find free EPA practice exams online at www.escogroup.org. Look on the main page for practice exams. Now, one of the most important concepts that you do have to know is the vapor compression refrigeration cycle. The compressor is the heart of the vapor compression refrigeration cycle. Low pressure, low temperature, superheated refrigerant vapor entering the compressor is compressed. It's changed to high pressure, high temperature superheated vapor. It then moves to the condenser where the heat is removed, de-superheating and condensing it into a liquid. Before it leaves the condenser, the liquid refrigerant is subcooled to a point below the liquid saturation temperature. It then flows to the metering device as a high pressure subcooled liquid. As the refrigerant flows through the metering device, the liquid is reduced to a low pressure, causing a small percentage of the liquid to flash to a vapor, known as flash gas. This lowers the remaining refrigerant to its saturation temperature. The low pressure, low temperature refrigerant flows into the evaporator as a low temperate liquid. As the refrigerant absorbs heat, it evaporates into a low temperature vapor. During this process, the refrigerant vapor is superheated above its saturation temperature and enters the suction line. From the suction line, the refrigerant enters the compressor as a low pressure, low temperature, superheated vapor to repeat the cycle. The compressor and the metering device are the dividing points between the high and low pressure sides of the system. Notice the line, the dotted line. Everything to the right of the dotted green line on this slide is high pressure. Everything to the left is low pressure. The compressor is the heart of the vapor compression refrigeration cycle. Low pressure, low temperature, superheated vapor entering the compressor is compressed, changing it to high pressure, high temperature, superheated vapor. Next in line comes the condenser. There's 3 stages of the condenser. It desuperheats, then condenses, does a change of state, vapor to liquid, and subcools. Before it leaves the condenser, the liquid refrigerant is subcooled to a point below the liquid saturation temperature. Subcooling is a sensible heat change. Desuperheating is a sensible heat change. Condensing is a latent heat change. Then the refrigerant flows to the metering device as a high-pressure, subcooled liquid. As the refrigerant flows through the metering device, the liquid is reduced to low pressure, causing a small percentage of the liquid to flash to vapor, which is known as flash gas, lowering the remaining refrigerant to its saturation temperature. The low-pressure, low-temperature refrigerant flows into the evaporator as a low-tempered liquid with some flash gas. As the refrigerant absorbs heat, it evaporates into a low-temperature vapor. Before the refrigerant vapor exits the evaporator and enters the suction line, additional heat superheats the vapor above its saturation temperature. Accessories shown in the basic diagram are the liquid receiver and a suction accumulator. Use of these components depends on the system design and/or the type of metering device used. A system that uses a thermostatic expansion valve, TEV, is usually equipped with a receiver located in the liquid line directly following the condenser. The system that uses a thermostatic expansion valve, TEV, TXV, cap tube, or fixed bore metering device may be equipped with an accumulator located in the suction line, which prevents liquid from entering the compressor. In air conditioning, you don't often see the liquid receiver. You see this more in refrigeration. In air conditioning, you don't often see the suction accumulator unless you are dealing with a heat pump system. But just be aware that these are there sometimes. The accumulator prevents liquid refrigerant from getting to the compressor. The liquid receiver makes sure that the metering device is only receiving liquid. Before using a recovery machine, you should always check the service valve positions. Notice the black section of the valve is what opens in the back seated position. The line port and the compressor port are open and the service port is closed. The black solid color in this diagram is where refrigerant will flow. This valve is in the normal position for normal operation, which is called back seated. A service valve can be in a front-seated position as well. Okay? When the service valve is in the front-seated position, the black solid color is where the refrigerant will flow in the front-seated position. The line port is closed, and the compressor port is open to the service valve. Service valve in a cracked position, or otherwise known as mid-seated. All 3 connections are open in the cracked or mid-seated position. The line port, the compressor port, and the service port is all open. This is the position for servicing and checking pressures. So most often, you're going to either be in this mid-seated position or in the normal run position. You do not run equipment with the discharge valve, that's the high side off the compressor, ever in the front seated equipment. You'll blow the compressor up. One of the most important tools for an HVAC technician is the gauge manifold set. The left side, which is most often blue, is a compound gauge. The right side, which is most often red, is a high pressure gauge. They're attached to the manifold to measure system pressures. Hoses are used to connect the manifold to the refrigeration system access ports or service valves to gain access to these pressures. The compound gauge measures low pressure in pounds per square inch gauge, PSIG, and vacuum in inches of mercury. The high side pressure gauge measures high side discharge pressure. Depending on refrigerant, the high side pressure gauge may be rated at 5 to 800 psi. The manifold is also equipped with a center port, usually a yellow hose, that can be connected to the recovery device, evacuation vacuum pump, or charging device. The compound gauge measures low pressure, PSIG, and vacuum in inches of mercury. It's normally blue color. The gauge is not intended to read deep vacuums, and there's what's known as a retard section of the gauge that is to prevent damage in case the gauge is connected to pressures greater than the rated pressure. The high pressure gauge measures high side discharge pressures. It's normally red in color. Atmospheric pressure is 0 psi or psig. Depending on the refrigerant, the high pressure gauge may be rated at 500 or 800 psi. An electronic gauge manifold or gauge may have combined temperature probes to measure refrigerant line temperatures for calculating system superheat and subcooling. These gauges, most of these gauges also will measure deep vacuum in microns. The EPA recommends that hoses be equipped with low loss fittings or valves that manually close or which close automatically to minimize the refrigerant loss from the hoses when they're disconnected. The hoses used for service and with recovery equipment must be equipped with low loss fittings. Minor releases when connecting or disconnecting hoses for service or recovery are considered to be a de minimis release. This is a pretty important term. You may only have de minimis releases of refrigerants. So the whole purpose of the Clean Air Act is to prevent environmental damage specifically to the ozone layer. Okay, there are 14 topics in the core contents with regard to ozone: stratospheric ozone depletion potential, Clean Air Act, Montreal Protocol, the 3 R's, the recovery devices, sales restrictions, refrigerants and oils, recovery techniques, leak detection, dehydration, recovery cylinders, safety, shipping and transporting. So let's first talk about the stratospheric ozone depletion. The stratosphere is what we consider the Earth's security blanket. It's located between 70 and 30 miles above sea level. The stratosphere is comprised of ozone and other gases. The introduction of chlorofluorocarbons, which is CFCs, and hydrochlorofluorocarbons, HCFCs, have dramatically changed our lifestyle. ASHRAE's safety classification of A1, the safest for most of the common refrigerants, does not consider the environmental effects. Little did we know that the use and release of these compounds into the atmosphere would have far-reaching long-term effects on our environment. The greatest effect is in the stratosphere, far removed from the Earth's surface. The ozone hole image shows very low values centered over Antarctica on October 4th, 2004. The biggest hole was recorded in 2006. So let's look at the stratosphere, or the Earth's atmospheric layers first. Based on the vertical temperature distribution of the Earth's stratosphere, 4 semi-horizontal layers or spheres can be distinguished: the troposphere, stratosphere and mesosphere, and the thermosphere. The stratosphere and mesosphere together are called the middle atmosphere, and their region also overlaps with the ionosphere, which is a region defined based on electrical charges of particles there. The stratosphere is part of the Earth's atmosphere, which extends from the top of the stratosphere from 7 miles to about 30 miles above the surface. This is the part of the atmosphere we're concerned about. Stratospheric ozone is a naturally occurring gas that filters the sun's UV radiation. It acts as a shield in the stratosphere. It protects life on Earth from the sun's UV rays. One ozone molecule consists of 3 oxygen atoms, which is O3, and protects us from harmful ultraviolet radiation and helps maintain stable Earth atmospheres. The UV radiation from the sun shears the chlorine atoms from a CFC or HCFC model. This chlorine atom is then attracted to an ozone molecule. So when we let refrigerant that has chlorine in it, so that would be a CFC or HCFC, the UV radiation from the sun breaks that chlorine atom from the CFC molecule, and that chlorine atom is then attracted to the ozone molecules. Stratospheric ozone depletion is a global issue that can lead to problems such as crop loss, increase in eye disease, skin cancer, reduced marine life, deforestation, increased ground level ozone. It is a global problem. It cannot be controlled by one single country. It's a global issue. CFCs and HCFCs, which is chlorine, fluorine, and carbon for the CFCs, and HCFCs, hydrogen, chlorine, fluorine, and carbon, which contain chlorine, have been found in air samples taken from the stratosphere. When CFCs and HCFCs are released into the atmosphere, the chlorine in them causes depletion of the ozone layer. The chlorine atom that breaks from the refrigerant molecule breaks and attaches itself to an oxygen atom from the ozone molecule. This forms a compound called chlorine monoxide, ClO, and leaves an O2 molecule. The chlorine monoxide will collide with another ozone molecule, releasing the oxygen atom, forming 2 O2 molecules, and leave the chlorine free to attack another ozone molecule. A single chlorine atom can destroy up to 100,000 ozone molecules. That is an extremely important number for those of you taking the exam. A single chlorine atom can destroy 100,000 ozone molecules. There's been a great deal of controversy over the subject of ozone depletion. Some believe that the chlorine found in the stratosphere comes from natural sources such as volcanic eruptions. However, air samples taken over erupting volcanoes show that volcanoes contribute only a small quantity of chlorine as compared to the refrigerants containing chlorine. The rise in chlorine measured in the stratosphere over the past 2 decades matches the rise in the amount of fluorine, which has a different natural source than chlorine, over the same period. Also, the rise in chlorine measured in the stratosphere over the past 20 years matches the rise in CFC and HCFC emissions over the same time period. The evidence is pretty clear that chlorine-containing refrigerants have changed the natural balance, thus depleting the ozone layer. Unlike other chlorine compounds and naturally occurring chlorines, the chlorine in CFCs will neither dissolve in water nor break down into compounds that dissolve in water, so it does not rain out of the atmosphere. Okay, so let me repeat that because this continues to come up in questions. This is not like chlorine that is in swimming pools. Unlike other chlorine compounds and natural occurring chlorine, the CFCs will neither dissolve in water nor break down into compounds that dissolve in water, so it does not rain out of the atmosphere. These chlorine molecules stay. Ozone depletion potential, ODP, is a measurement of substances such as CFCs, HCFCs, ability to destroy ozone. CFCs have the highest ODP. HFCs are made up of hydrogen, fluorine, and carbon. They do not contain chlorine that affects the ozone layer, but they do have a higher global warming potential. So again, let me repeat this. Ozone depletion potential is a measurement of substances such as CFCs and HFCs' ability to destroy ozone. The key is chlorine. HFCs, which are the newer refrigerants, are made up of hydrogen, fluorine, and carbon. They do not have an ODP because there's no chlorine, but they do have a global warming potential. Greenhouse gases, CHGs, warm the Earth in two ways. They absorb energy, slowing the rate at which it escapes to space, and act like a blanket insulating the Earth. Examples of greenhouse gases and their effects on the atmosphere are, one of them is R744, carbon dioxide, CO2. It's a natural gas. Very high pressure refrigerant, R744, with a 0 ODP, it can have a global warming potential of 1. The addition of man-made CO2 creates an overabundance and results in excess CHGs that enter the atmosphere as a result of burning fossil fuels. For example, coal, natural gas, and oil, solid waste, wood products, and certain chemical reaction. Carbon dioxide is used as a very high pressure HC refrigerant, 744, with 0 ODP and a global warming potential of 1. R744 is used primarily in commercial and industrial process and does not require Section 608 certification for purchasing or service. Flammable refrigerants require red color marking on all process tubes and other pipes through which flammable refrigerant passes and the service connection. The color marking must extend 1 inch in both directions from service locations. Okay, we're starting to have more and more flammable refrigerants in the market. One of these examples is propane, R290. Used as a refrigerant, must meet the purity standards set forth for our HVAC equipment. Propane purchased for grilling contains impurities which will damage refrigeration equipment. Propane and isobutane, R600A, are examples of A3 flammable refrigerants that do not require recovery. When you see flammable refrigerants, R290 and R600A, they have a classification of A3, which means they're extremely flammable. You will not recover these equipment. If any flammable refrigerant is covered, a grounded explosion-proof recovery machine must be used. Fluorinated gases such as CFCs, HCFCs, HFCs are required to high global warming potential gases. Okay? They are emitted from a variety of industrial processes. And we use fluorinated gases because the F in each of our refrigerant is fluorine. Okay, so all of the refrigerants we use that have the F in them are considered high global warming potential gases. R245FA is an HFC with 0 ODP and a global warming potential 1,030 times greater than carbon dioxide. It's a low pressure refrigerant used in commercial industrial process chillers in place of R11 and foams. Okay, so if you're using this gas, it has a 0 ODP because there's no chlorine in it, but it has an extremely high GWP, 1,030 times higher than carbon dioxide, which has a GWP of 1. R134A is an HFC with an ODP of 0 and a global warming potential 1,430 times greater than carbon dioxide. R134A is a medium range pressure refrigerant. It's used in auto, domestic refrigeration, and commercial industries. You'll always recognize it because it's in this sort of light green cylinder. R410A is again a hydrofluorocarbon. It's an HFC refrigerant with an ODP, because there's no chlorine in it, of 0, and a global warming potential 2,090 times greater than carbon dioxide. It's a near azeotropic refrigerant that does not fractionate during phase change in an HVAC system. One disadvantage of R410A is the operating pressures are approximately 50 times higher than R22 and cannot be considered a drop-in replacement for retrofitting existing equipment. Primarily, you will see this in comfort cooling. That's package units, residential split systems, and now some window units and dehumidifiers as well. R1234YF is a medium pressure HFO refrigerant with an ozone depletion potential of 0 and a global warming potential only 4 times higher than carbon dioxide. R1234ZE is a medium pressure, used in new chillers, heat pumps, and vending machines. R123ZD is a low pressure version of the hydrogen gases used in new chillers and foam blowing. So we've talked about some of the ASHRAE codes so far, but ASHRAE grouped refrigerants by class and flammability, into a safety group. So refrigerant classification, the A is the safest, B is extremely toxic to humans, so we have a choice of A or B. Then we have either flammable, we have no flammability, slightly flammable, low flammability, or high flammability. So A1 is going to be my safest refrigerant ever. B1, it's toxic to humans. In other words, you don't want to breathe this in or come in contact with it, but still no flammability. My most dangerous refrigerants are the B3, which is extremely flammable and very toxic. Okay, let's talk a little bit about the Clean Air Act, Title 6. Companies or service technicians who violate Clean Air Act provisions may lose their certification and be required to appear in federal court and be fined up to $44,539 per day per violation. The EPA may require technicians to demonstrate the ability to properly perform refrigerant recovery and recycling procedures. Failure to demonstrate these skills can result in revocation of certification. Technicians not following stricter state and local government requirements may lead to other penalties. What this boils down to is EPA sets a minimum standard. Any state or local government may be able to set higher standards as a part of their building codes. State and local jurisdictions may impose regulations that are equal to or greater than those under EPA Section 608. Natural refrigerants such as R744, which is carbon dioxide, that do not pose a threat to health or the environment according to the EPA, may be released back into the environment. It is in a violation of Section 608A to falsify or fail to keep required records, fail to reach required evacuation levels prior to opening or disposing of appliances, knowingly release or vent ozone depleting and substitute refrigerants such as CFCs, HCFCs, or HFCs while maintaining, installing, repairing, or disposing of appliances or industrial process refrigeration, with the exception of a de minimis release. De minimis is defined as so small or minimal indifference that it does not matter and the law does not take it into consideration. It is in violation of 608 to service, maintain, or dispose of appliances designed to contain refrigerants without being appropriately certified. Fail to recover regulated refrigerants before opening or disposing of an appliance. In other words, recover refrigerants and be certified to do so. It's in violation of Section 608 to fail to have an EPA-approved recovery device equipped with low-loss fittings that automatically close or have manually operated shutoff valves on the hoses. It is in violation of Section 608 to add nitrogen to a fully charged system for the purpose of leak detection and thereby causing release in the mixture. As we talk about leak detection, you're allowed to use a little bit of refrigerant mixed with nitrogen for the purpose of leak detection with electronic leak detectors. However, you cannot add nitrogen to a fully charged system because you will not be able to recover that refrigerant and you'll have to release the entire thing into the air. It's in violation of Section 608 to dispose of refrigerant cylinders without first recovering them to 0 psi to recover any refrigerant remaining in the cylinder. It's in violation of 608 to release refrigerant during vandalism or theft of any HVAC equipment. In other words, if someone steals for copper, they're not only violating local laws and state laws because of theft, but they're actually violating federal laws that they can be prosecuted under. It's the responsibility of the final person in the disposal chain to ensure that the refrigerant has been removed from the appliance before scrapping. Technicians disposing of appliances with 5 to 50 pounds of refrigerant must keep the following records: the location, date of recovery, and the type of refrigerant recovered for each disposed appliance. The quantity of refrigerant by type recovered from disposed appliances in each calendar month. The quantity of refrigerant and type transferred for reclamation or destruction, and to the person who it was transferred and the date of the transfer. In other words, you have to keep a refrigerant log. And you have to account for the refrigerant you recovered, where it was from, and then when you turn the cylinder into the supply house or a refrigerant recovery service, you have to have records of how much, when, and who it was transferred to. The Montreal Protocol occurred in September of 1987. 24 nations met. It's an international treaty. Following several years of negotiation, an international agreement or treaty regulating the production and use of CFCs, HCFCs, halons, methylchloroform, and carbon tetrachloride entered into force in mid-1989. It's known as the Montreal Protocol. This landmark agreement initially required a production and consumption freeze. The Montreal Protocol called for stepwise reduction and eventual production phase-out of various ozone-depleting substances in developed countries. In the United States, CFCs was the first substance group that was phased out of production. HCFC refrigerants is scheduled for phase-out in 2020, when virgin supplies of restricted refrigerant are depleted. Future supplies will come only from recovered, recycled, or reclaimed refrigerants. The 3 R's that are going to be discussed is the process of recovery, recycling, and reclaiming. Okay, these sound similar, but they're in fact quite different. Recovery is to remove refrigerant in any condition from an appliance and store it in an external container. Okay, from that external container, it can be put back into the same system, recycled, or reclaimed. Recycling is to clean the refrigerant for reuse by separating the oil from the refrigerant, removing moisture and other contaminants from a refrigerant by passing it through 1 or more filter dryers. Recycled refrigerant must meet ASHRAE 700 standards before they can be reused in a system owned by someone else. Again, refrigerant that is just recovered cannot change owners. Recycled, once restored to meet ASHRAE 700, which is new refrigeration standards, it can be used in a system owned by someone else. Reclaiming is to process the refrigerant to a level equal to new virgin project specification as determined by chemical analysis. Reclaimed refrigerants must meet ASHRAE 740 standards before they can be reused. So again, recovery, that's just the process of removing it and storing in an external container, and it can be put back into the same system or a system owned by the same individual. Recycling, it's cleaning up by passing through a number of filter dryers. Okay, once it's clean according to ASHRAE 700 standards, it can be sold to a different individual. Reclaiming has to be shipped to a chemical plant and reclaimed to new standards before they can be reused. Refrigerant recovery devices and recycling equipment manufactured after November 15, 1993 must be certified and labeled by an EPA-approved equipment testing organization to meet EPA standards. Okay, and right now in the marketplace, you're not going to find much equipment that was manufactured before November 15, 1993. There are two basic types of recovery devices. You have system-dependent and self-contained. System-dependent captures refrigerant with the assistance of the components in the appliance from which the refrigerant is being recovered. In other words, the compressor has to be working. Self-contained, okay, has its own means to draw the refrigerant out of the appliance. In other words, it has a compressor internally to it. The sale of CFC, HCFC refrigerants has been restricted to certified technicians since November 14, 1994. The sale of ozone-depleting substances and substitute refrigerants such as HFC and HFO refrigerants is restricted to certified technicians as of January 1, 2018. Only technicians who are certified under Section 609 of the Clean Air Act, Motor Vehicle Conditioning, are allowed to purchase refrigerants in containers smaller than 20 pounds. The sale of CFC and HCFC refrigerants has been restricted, okay, since November 1994. The sale of ozone-depleting substances and substitute refrigerants, HFC and HFO refrigerants, is only to certified technicians of January 1st, 2018. EPA's Significant New Alternative Policy, SNAPS, identifies and evaluates substitute refrigerants. EPA must review and approve any new refrigerants before they're introduced into air conditioning equipment. EPA also talks about substitute refrigerant and oils. EPA's classifications and decisions on alternate substitutes may be listed as acceptable, acceptable subject to use conditions, acceptable subject to narrow use conditions, and unacceptable alternatives. R134 is an HFC and is considered ozone friendly. There's no such thing as a drop-in refrigerants. The oils used in most HFC and HFO refrigerants are esters. Esters cannot be mixed with other oils. So even though R134A takes the place of R12, it is not a drop-in. It's also important to remember when leak testing an R134A system to use pressurized nitrogen. EPA and compressor manufacturers must approve a refrigerant for use. Any change in a refrigerant type in a system will change the operating characteristics of that system and can also void the warranty. Do not be the mechanical engineer that overrides what a company's warranty says. It's also important to remember, again, to use nitrogen with only a trace amount of refrigerant vapor. In order to avoid contamination, use the same refrigerant as the system charge. This is not considered to be a refrigerant that must be recovered if you're only using trace amounts. There are several refrigerant blends commonly in use. Some of the blends are called ternary, which are considered a three-part blend. Ternary refrigerants are used with synthetic alkylbenzene lubricants. Make certain that you're using the correct oil for the refrigerant. Most of these blends have a temperature glide. Substitute refrigerants and oils, okay, are hygroscopic. Hygroscopic oil has a high affinity for water. Some of these oils can absorb water through a plastic container. An oil sample shall be taken and analyzed if a system has had a burned out compressor, winding failure, or major leak allowing moisture to enter the system. We want to test that refrigerant oil. Refrigerant blends that are made up of two or more single component refrigerants. Depending on how strongly the refrigerant molecules are attracted to each other, they may be classified as azeotropic or zeotropic. An azeotropic mixture acts like a single component refrigerant over its entire temperature pressure range. It does not have a temperature glide. A zeotropic blend, it behaves like a mixture of individual components with predictable properties based on the combinations. Okay? It does have a temperature glide. A temperature glide refers to the refrigerant blend that has a range of boiling points or condensing points throughout the evaporator and the condenser process. Refrigerant fractionization can occur from a continuous leak due to differences in pressures and from the combined refrigerants. Okay, what this is basically saying is a zeotropic refrigerant has a temperature glide. Okay, if there is a leak in the system, the different components are going to leak out at different rates. You cannot just top the refrigerant off because you don't know what's actually left in that system. R400 series of refrigerants are blended, and the components of a blended refrigerant can leak from a system at uneven rates due to different pressures. Then a percentage of the refrigerant blend changes due to leaking. This out of balance refrigerant is said to be fractionated. The proper charging method for blended refrigerants is to weigh it in on the high side of the system as a liquid. When adding refrigerants to an undercharged system, liquid is throttled into the low side while the system is operating. You never put refrigerant into the high side of a system while it's running. The bubble and dew points are used to indicate the condensing and evaporation temperature for blended refrigerants on a pressure temperature saturation chart. Bubble point is used when charging by condenser subcooling, and dew point is used by charging suction or evaporator superheat. This relationship to pressures and temperatures based on the refrigerant's temperature glide. Temperature glide can range from a few tenths of a degree to 12 degrees or more. Even though the pressure-temperature relationship and the operating characteristics may almost be the same, refrigerants cannot be interchanged to the flammability of some of the HC and HFOs. The equipment must be designed to handle the refrigerant. Therefore, EPA regulates the maximum amount of refrigerant that can be used in the new systems by their type and use. EPA regulations require a service apparature or process stub on all hermetically sealed appliances that use a regulated refrigerant in order to make it easier to recover refrigerant. Do not mix refrigerants in the recovery cylinders. If you discover that 2 or more refrigerants have been mixed in the system, you must recover the refrigerant into a separate tank. Mixtures may be impossible to reclaim. Badly contaminated mixed refrigerants must be destroyed at your expense. If a strong odor is detected during the recovery process, a compressor burnout has likely occurred. When recovering refrigerants from a system that experienced a compressor burnout, watch for signs of contamination in the oil. After recovering refrigerant, if nitrogen is used to flush the debris out of the system, nitrogen may be legally vented. A suction line filter dryer should be installed to trap any debris that may damage the new compressor. The size of the equipment, the amount of moisture, the length of hose between the unit being recovered and the recovery machine, and the ambient temperature can all affect the efficiency of the recovery process. Long hoses will cause excessive pressure drop, increased recovery time, and have a potential for increased emissions or venting from the recovery machine. Excessive venting of the recovery machine or cylinder is illegal. Since all refrigerants have a pressure-temperature relationship, the lower the ambient temperature surrounding the equipment being serviced, the slower the recovery rate will be. After completing the transfer of liquid refrigerant between a recovery unit and a refrigeration system, you should guard against trapping liquid refrigerant between the service valves. Recovered refrigerant may not meet ASHRAE standards for virgin refrigerants, and therefore can only be reused in the same system or another system of the same owner. Recovered refrigerant cannot change ownership. In order to determine the general area of a leak, use an electronic or ultrasonic leak detector after pressurizing the system with nitrogen and a trace amount of refrigerant. Once the general area of the leak is located, the use of soap bubbles will aid in pinpointing the leak. Finding or repairing leaks in a system will conserve refrigerant for future use. 2 verification tests are required when an appliance has more than 50 pounds of refrigerant or has triggered the leak rate threshold and subsequently been repaired. One must be performed before the appliance is recharged, and one after the appliance returns to its normal operating condition. Industrial process refrigeration, IPR, refers to refrigeration equipment used in agriculture, crop production, oil and gas extraction, ice rinks, manufacturing of frozen foods, dairy products, food and beverages, ice, petrochemicals, chemicals, machinery, medical equipment, plastics, paper, and electronics. When an appliance is designated for multiple use, the category will be considered industrial process refrigeration if 50% or more of its operating capacity is used for industrial process refrigeration. Dehydration or evacuation, comes next. So you've recovered the equipment, you've fixed the leak, you've leak checked it, now you're going to dehydrate it. The reason for dehydrating a refrigeration system is to remove water and water vapors. It's important to follow proper dehydration procedures. If moisture is allowed to remain in the operating refrigeration system, hydrochloric and hydrofluoric acids may form. Evacuation of a system is the suggested method for dehydration. It's not possible to over-evacuate systems. Most manufacturers require evacuation to 500 microns or lower. The factors that affect the speed and efficiency of evacuation are size of equipment being evacuated, the ambient temperature, the amount of moisture in the system, the size of the vacuum pump and suction line. In addition, vacuum lines should be equal or larger than the pump intake connections. The piping connection to the pump should be as short as possible and as large in diameter as possible. You want to move as much air and gases as possible. Measuring a system's vacuum should be done with the system isolated, the vacuum pump turned off, and the vacuum gauge connected as far away as possible from the vacuum pump. Dehydration is complete when the vacuum gauge shows that you have reached and held the required finished vacuum. You can heat the refrigeration system to decrease dehydration time. Tapping a compressor with a rubber mallet will also aid in releasing trapped refrigerant from the oil. Word of warning, and very important, never operate the compressor while the system is in a deep vacuum. You can actually create internal electrical arcing, and it can burn out the motor windings. This chart is used to show the relationship of pressure in microns, inches of mercury, and vaporization temperatures for water. At 500 microns, which is the highlighted lines, water will vaporize at any temperature above negative 12 degrees. So again, what we're trying to do is we're putting into a significant vacuum and we are lowering the pressure, okay, and therefore lowering the boiling point of the water. So we lower that pressure enough, we put it in a high enough vacuum, we now are going to boil water at negative 12 degrees. The low recovery cylinders differ in many ways from disposable cylinders. Disposable cylinders are used with virgin refrigerant only and may never be used for recovery. Disposable cylinders have a one-way valve. Refrigerant can come out, they cannot go back in. Recovery cylinders are specifically designed to be refilled. Recovery cylinders have two ports, one liquid, one vapor. Care must be taken not to overfill or heat these cylinders or it could cause an explosion. The EPA requires that refillable refrigerant cylinders must not be filled above 80% of its capacity by weight, and the safe filling level must be controlled by mechanical float devices, electronic shutoff devices, or weight. Refillable cylinders must be DOT, that's Department of Transportation approved. That's important, it's on the exams. Approved refrigerant cylinder recovery cylinders can be easily identified by their colors, yellow tops, and gray bodies. All refrigerant recovery cylinders should be inspected for rust. If a refillable cylinder shows sign of rust or appears to be heated or damaged in any way, it should be reduced to 0 psi by recovering to another cylinder and discarded. Reclaimers will not accept visibly burned tanks. Recovery cylinders are specifically designed to be refilled. Care must be taken not to overfill or heat these containers, just they can cause an explosion. Again, if recovery cylinders need to be inspected occasionally. If they show rust or appear not to be secure, they should be discarded after recovering them. Refillable cylinders used for transporting recovered pressurized refrigerant must be DOT, Department of Transportation approved. You have to take a little bit of safety into account as you're working with it. The EPA is concerned not only with the prevention of refrigerant venting, but the technician's overall safety. When handling, filling refrigerant cylinder or operating recovery or recycling equipment, you need to wear safety glasses, protective gloves, and follow all equipment manufacturer safety procedures. Make sure the recovery machine is grounded when in use, especially when recovering a flammable refrigerant. You do not want any stray voltages. When pressurizing a system with nitrogen, you should always charge through a pressure regulator and insert a relief valve in the downstream line from the regulators. Relief valves cannot be installed in series. If corrosion buildup is found within the body of a relief valve, the valve must be replaced. When leak checking a system, never pressurize the system with oxygen or compressed air. When mixed with refrigerants, oxygen or compressed air can cause an explosion. To determine the safe pressure for leak checking, check the equipment data place for the maximum low side test pressure. Go to the evaporator, find the data plate, and find out what the maximum low test pressure is. That's going to be your low side of the system. When using recovery cylinders and equipment with Schrader valves, it's critical to inspect the Schrader valve core for leaks, bends, and breakage. Replace damaged valve cores to prevent leakage, and always cap Schrader ports to prevent accidental depression of the Schrader valve core. In event of a large release of refrigerant in a confined area, a self-contained breathing apparatus is required. If a large leak of refrigerant occurs in an enclosed area and self-contained breathing apparatus is not available, immediately vacate and ventilate the area. In large quantities, all refrigerants can cause suffocation because they displace oxygen. Inhaling refrigerant vapors or mist can cause heart irregularities, unconsciousness, and oxygen deprivation, leading to death. You can drown in refrigerant because you will not be able to breathe. Never expose refrigerants to open flame or glowing hot metal surfaces. At high temperatures, refrigerants can decompose and form acids. Hydrochloric acid is formed if refrigerant contains chlorine, and hydrofluoric acid is formed if the refrigerant contains fluorine. If oxygen is present, it's also possible to form carbon monoxide, carbon dioxide, and phosgene gas. If a hydrocarbon refrigerant is released into a space, an explosion can occur if the refrigerant concentration is above the lower flammability level and below the upper flammability limit with an ignition source. That's hydrocarbon refrigerants. That's the propane type refrigerants. If moisture is allowed to remain in an operating refrigeration system, hydrochloric and hydrofluoric acid may form. Evacuation of a system is the suggested method of dehydration. It is not possible to over-evacuate a system. In large quantities, all refrigerants can cause suffocation because they displace oxygen. Inhaling refrigerant vapors or mist may cause heart irregularities, unconsciousness, oxygen deprivation, leading to death. Always review the safety data sheets, that's the SDS, when working with any solvents, chemicals, or refrigerants. Silicon emulsifiers for use in seals or gaskets are not compatible with HFO refrigerants. Before shipping any used refrigerant cylinders, check that the cylinder meets DOT standards. Complete the shipping paperwork, including the number of cylinders of each refrigerant, and properly label the cylinder with the type and amount of refrigerants before returning for reclaiming. Cylinders should be transported always in an upright condition. Once it is shipped, it is regulated by Department of Transportation standards. Each cylinder must be marked with a DOT classification tag, including it is either flammable or non-flammable gas. Some states may require special shipping procedures to be followed based on their classification of used refrigerants. Check with the Department of Transportation in your state. Okay, this chart depicts the old and new refrigerants, the type of refrigerants, the ODP, the GWP, okay, the EPA pressure range, and the ASHRAE class. Your most common refrigerants right now you're going to find is R22, which is an HCFC. It's used in a lot of air conditioning and medium temperature refrigeration system. Okay, it's considered a high pressure and it's an A1. 134A is an HFC, has a 0 ODP, has a pretty high GWP. It's used in automotive, domestic, and commercial refrigeration. Okay, it's considered a medium pressure refrigerant. 410A. Okay, let's go back. Okay, 410A is also on the chart, and it is the replacement for R22. Let me pull that chart back up here. Sorry about that. Okay, it's 410A. It's an HFC, same class, same type as 134A. As 0 ODP, it's used in air conditioning. It's considered a high pressure refrigerant, and it's an A1. Now, you have some hydrocarbon refrigerants, and you'll know these names if you deal with any type of gas heating: ethane, propane, isobutane. These are considered a flammable rating of 3. Be very careful with these refrigerants. Okay, you cannot recover them using the standard recovery equipment. You have to ground everything, and if you end up servicing these equipment and have to do leak repairs, you need some special training on this to not you have to prevent an explosion hazard. In the next set of videos, we'll do type 1, type 2, type 3. This is by far the longest because this was the core and the basics that appear on the EPA exams.